Hello. In this video we're going to be looking at one particular aspect of linear models in R. What we're going to be looking at is something that a lot of people have problems with, and that's understanding the coefficients table that you get when you fit a linear model in R. We're going to be looking at the case of analysis of variance type analyses in particular, and we'll start with just a single factor analysis of variance. Then we'll look at a two-factor analysis of variance without an interaction term, and then we'll move on to the case where it gets particularly complicated, a two-factor analysis of variance with an interaction term. So let's kick off with an example. This is going to be a single factor ANOVA, and this is just an example that I've made up. Let's say you're looking at drug effects on systolic blood pressure. You've got three different drug treatments, A, B and C. You've got a control, which is no treatment. You've got 30 subjects per group. You've given them all either A, B or C or a placebo for the control, and you've measured their systolic blood pressure. So you've got these data and you want to fit an ANOVA and look at the output of the ANOVA and try to understand what's happening in your data. So you can generate the summary table that you get in R by using the summary function on your fitted linear model, and when you do that you get this rather large and intimidating set of output. So let's just go through this and have a look at some of the things that the summary table is telling us. First of all, it tells us what the actual model we fitted was. That might sound like it's a bit obvious and unnecessary, but in some cases where you're fitting lots of different statistical models, this can be really useful just to let you check. Secondly, it gives you a quick and dirty summary of the residuals of the model, and you can use this at least to check whether your residuals are centered around zero and roughly symmetrical around zero. So it's a quick check on something that you probably want to check in more detail with some diagnostics later. And just looking at this, you can see that our median is pretty close to zero. We've got the first quartile and the third quartile, and you can see those are approximately symmetrical around our median. And then the minimum and maximum values, again, are roughly symmetrical, and it doesn't look like there's anything particularly outlandish there. That's hardly surprising because I did actually generate these data with a random number generator. But that just lets us have a quick check on the residuals before we go any further. Then if we go down at the bottom, we've got a bunch of different stuff, but what's probably the most important is the R squared value, which tells us the proportion of variance that our model is explaining. And then finally, it gives us the F statistic for the entire model. So for a single factor ANOVA, this would be the same as the F statistic and the p-value that you would get just for your factor in the ANOVA table. For a multiple factor ANOVA or for other kinds of linear models, it's going to be the F statistic for the entire model. So it's not telling you anything about the significance of particular factors. Okay, so those are the other things that we get in the summary table, but then in the middle there's this thing, which is what causes all the confusion and the trouble, and this is the coefficients table, and a lot of people have a lot of difficulty in understanding what this is and interpreting it. So the rest of this video is going to be devoted to the coefficients table and trying to explain how it works. So here's that coefficients table again. What's it actually telling us? Well, the coefficients table is giving us a set of what are called treatment contrasts. So when we're fitting a linear model, we don't get every single contrast between every single factor level, because if we wanted to do that, we could just use something like a Tukey's HSD test or another multiple comparisons test, and that would then give us all the problems with normal multiple comparisons. The treatment contrasts actually kind of fall out of the way that the linear model is calculated, and they give us a limited set of comparisons that we can make between treatment levels. And once you understand what these treatment contrasts are and how they're working, you can use them to interpret the output of your model. So let's go through this. These are the treatment contrasts, or the coefficients table for our single factor ANOVA, and at the top we've got a line that says intercept, and again, you're fitting an ANOVA. There isn't an intercept like there is with a linear regression. What is going on? Well, the answer is that there is kind of an intercept when you're fitting a linear model with just factors. It just doesn't make as much sense as the intercept for something like a linear regression. What you need to know about the intercept here is that the intercept is actually the mean for the reference level of our factor. So when we have a factor in R, the factor has a reference level, and that reference level by default is the level which comes first in alphabetical order. So the levels for our factor here are A, B, C and control. A comes first in alphabetical order. So that intercept there is the estimated mean for our data from factor A. So the mean for factor A is 148.32. And then the remaining rows of the coefficients table, because this is just a single factor ANOVA, are the contrasts between the other factor levels and the reference level. So let's just go through that one at a time. So we have treatment B, and we have a value called estimate, and that estimate is the difference between the mean for treatment B and the mean for treatment A, or in other words, the difference between the mean for treatment B and the reference level. So if you're trying to think about the effects of your treatment, this is telling us about the effect of treatment B when it's compared with treatment A. And so we can use that to calculate an estimated mean for treatment B, which is 148.32 minus 4.09, which is 144.23. The estimate for treatment C is, once again, the difference between the mean for the reference level, treatment A, and the mean for treatment C. So again, this is telling us what the effect of treatment C is when we compare it with treatment A. And again, we can calculate the estimated mean for treatment C, which is 148.32 plus 2.01, which gives us 150.33. And then finally, we have treatment control. And this is once again giving us the contrast between the control level and the reference level, which is treatment A. So again, we can calculate the mean for our control level, and that is 148.32 plus 2.06, which is 150.38. So that's what those figures in the estimate column of the coefficients table mean. If we take those estimated means from our coefficients table that we've calculated and we compare them with the actual means that we can calculate for our data, you can see that those numbers are the same. What about the other thing that's in that coefficients table? The marginal p-values. So we have an estimate, we have a standard error, we have a t-value, and then we have a p-value. The t-value is simply the estimate divided by the standard error, and then the probability, or the p-value, is derived from that t statistic. So what do these marginal p-values mean? Well, that one there, the one for the intercept, is telling us that our intercept is significantly different from 0, which isn't particularly helpful. But what about the next one, the one for treatment B? Well, remember that this is a table of contrasts, so the treatment B line is telling you about the effect of treatment B when compared to treatment A. That very small p-value there is telling us that the effect of treatment B is significant when you compare it to treatment A. In other words, the mean for treatment B is significantly different from the mean for treatment A. What about the other two that we have? Well, neither of those values is lower than 0.05, so neither of them are significant. Recall that these are contrasts with our reference level. So the 0.07 value for treatment C and for the control treatment level are telling us that neither of these are significantly different from treatment A. In other words, if you're comparing the effect of treatment C or the effect of the control with treatment A, neither of those factor levels has a significant effect. Okay, that's all very well, but in an experiment like this, we don't actually want to compare our treatment levels with each other. What we want to do is compare them with the control, so it would make a lot more sense if the reference level in this case was actually the control. And we can do that in R by using the Relevel function. So you can use Relevel to change the reference level for a factor. That's how you do it for treatment. And if you do that and then run your model again, you'll get a new coefficients table where the contrasts are now with the control rather than with treatment A. So our new reference level is control, and the contrasts that we're getting are now with the control. So this lets us compare the effects of the three different treatments we've used with our control rather than with treatment A, which is much, much more useful. So you can see that these numbers are now different and the p-values are now different, and that's because they're being compared with the control rather than with treatment A. And if you look at the marginal p-values, we can now see that treatment B has a significantly different mean from our control, which means that treatment B has a statistically significant effect when compared with the controls, but neither treatment A nor treatment C have a significant effect when compared with the control. And it's that comparison with the control that we're interested in and that's important in an experiment like this. Okay, that's the single factor ANOVA case. Let's move on to a two-factor ANOVA, and in this case we're going to be thinking about a two-factor ANOVA where we've not included an interaction term in our model. So we've got a similar set of data as before. It's not the same data, but what we've got now is we've got two age classes as well. So we've got a 40 to 50 age class and we've got a 70 to 80 age class, and we've given people from each of those age classes either drug A, drug B, drug C, or we've given them a placebo for our control. So if we pull up the summary table like we've done now, you can see that a lot is familiar and a lot is very similar to our previous summary table, but we've got a new line in the coefficients table, which is the age class 70 to 80 line. So let's just go through the coefficients and we'll see how this works in this particular case. So what we can do is we can work out what the estimated mean is for each combination of factor levels, and that will hopefully help us to understand how the coefficients table works. So the intercept is now the estimated mean for the reference level for both factors. So the reference level for the age class factor is 40 to 50 because lower numbers come first in alphabetical order, and we're retaining the reference level with control as the reference level for the treatment factor. So the mean for individuals given the placebo control age 40 to 50 is that value there, 149.3. The rest of the first bit of the coefficients table now works in exactly the same way as it did for the single factor ANOVA when we're thinking about the 40 to 50 age class. So the mean for treatment A is 149.3 minus 1.1. The mean for treatment B is 149.3 minus 4.35 or 4.36 if you round it properly. And the mean for treatment C is 149.3 plus 3.39. So if we're just thinking about the 40 to 50 age class, that first section of the coefficients table works in exactly the same way as the coefficients table for our single factor ANOVA, and we can calculate the means in exactly the same way, and the various p-values and the effect sizes or the estimated effects work in exactly the same way. So we can fill in those estimated means there. What about that last line? Well, that line is telling us the effect of going from the age class 40 to 50 to going to the age class 70 to 80. And because there's no interaction term in this model, that effect is estimated for all factor levels of our other factor. So if we're thinking about the estimated values, the estimated means for our 70 to 80 age class. They're simply the estimated means for the 40 to 50 age class plus 5.12. So for the intercept, for the reference level, the estimated mean is 149.3 plus 5.12. For treatment A, the estimated mean is the estimated mean for the 40 to 50 age class plus 5.12, and then the same for treatment B and for treatment C. So those means for the 70 to 80 age class are actually calculated from three separate values within the coefficients table. But the important thing about that age class 70 to 80 estimate is that that's the estimated effect for all factor levels of treatment of moving from age class 40 to 50 to age class 70 to 80. Okay, and if we compare those estimated means with the actual means that we can calculate from our data, what we'll find is that they're not actually exactly the same. So one example is the one I've circled here, where you can see that the two values differ slightly. And the reason those values are differing slightly is that because there's no interaction term in this model, we're not estimating a separate effect of age class for each treatment level. So we do get some slight differences with the actual means. The benefit, of course, is that we have a simpler model and we're using fewer degrees of freedom, so we have a more powerful statistical test. Okay, how about the final example, two-factor ANOVA with an interaction. So in this case, we've got an effect of age class that's varying between our treatment levels, and you can see that in this box plot here. So for the 70 to 80, for the control treatment and for treatment C, you can see that the differences between the two age classes are roughly the same. But then for treatment B, you can see there's a much smaller difference between the age classes. And for treatment A, there's a kind of intermediate degree of difference between the age classes. So the effect of age appears to be depending on treatment, or alternatively, the effect of treatment appears to be depending on age. And in that case, we need to use an ANOVA with an interaction term to get a proper model of what's happening in our data. And this now gives us a coefficients table like this, which is starting to get rather complicated and intimidating. So what we'll do is we'll just talk through what this coefficients table means, and hopefully you'll see how it relates to the simpler coefficients tables that we've been looking at already. So the intercept, once again, is giving us the mean value for the reference levels of our factors. The reference levels of our factors are control for the treatment factor and age class 40 to 50 for the age class factor. So that intercept is the mean for control treatment, age class 40 to 50. The first part of the coefficients table that follows that is once again pretty much the same as the coefficients table for a single factor ANOVA. So this is giving us the contrasts between treatments A, B and C and our control treatment for age class 40 to 50. The next line, age class 70 to 80, tells us the effect of moving from the first age class 40 to 50 to the second age class 70 to 80, but only when the treatment level is the reference level. So that value there, 9.09, is the difference between the 70 to 80 age class and the 40 to 50 age class when given the placebo control treatment. Then, finally, we've got these last three lines in our coefficients table, and these lines are referring to the interaction. It's often quite hard to understand what these lines in a coefficients table mean. Recall that when we have a significant interaction in an analysis of variance, what that means is that the effect of one factor or one explanatory variable depends upon the value of another factor. So in this case, you can think of these coefficients as telling us the difference in the effect of treatments A, B and C when you go from the younger age class, the 40 to 50 age class, to the older 70 to 80 age class. So for treatment B, for example, the effect of giving treatment B in the younger age class is that the mean systolic blood pressure is reduced by 2.61. So the effect is minus 2.61. When you give treatment B in age class 70 to 80, the effect is that the systolic blood pressure is reduced by minus 2.61, the effect at the first factor level, minus 8.75. So overall, treatment B in age class 70 to 80 reduces blood pressure by over 10 points. Let's move on and see how we can calculate the actual means for these final treatment combinations. So for controls and age class 70 to 80, it's straightforward. That coefficient is telling us the effect of going from age class 70 to 80 when we have the control treatment. So the final estimated mean for that combination of factor levels is 149 plus 9.09, which is 158.1. What about treatment A in age class 70 to 80? Well, we can start by calculating the effect of treatment A in age class 40 to 50, or the expected mean for treatment A in age class 40 to 50, which is 149 plus 0.48, those top two coefficients that I've marked there. Then we have the effect of age class, and then we have the difference in the effect of treatment A when you're in the upper age class, and that is minus 3.36. And so the overall mean for that combination is 155.21. Moving on to treatment B, once again we can calculate what the effect of treatment B is at age class 40 to 50, and that's 149 minus 2.61. Then we add the effect of age class, and then we have the difference in the effect of treatment B when you go from the younger age class to the older age class, which is minus 8.75. And that gives us a mean of 146.73. And then moving on to treatment C, the last one, we calculate this in the same way. So first of all, what's the expected mean when you're in the younger age class? It's 149 plus 0.85. Then we add the effect of age class, and then we have the difference in the effect of treatment C when you're going from age class 40 to 50 to age class 70 to 80. And that gives us a total mean of 159.51. One thing to remember about interaction terms is that they're actually symmetrical. So I've been explaining this as the difference in the effect of treatment when you go from one age class to the other one. You can think of it equally well as a difference in the effect of age when you go from one treatment to another one. But we're not going to get into that in detail because it would just make things especially confusing. If we look at the p-values, we can now think about the overall pattern in our data when we're thinking about treatment effects compared to controls and how that varies between the two age classes. Our first set of marginal p-values are telling us that for age class 40 to 50, none of these treatments actually has a statistically significant effect on systolic blood pressure. Treatment B has a p-value which is only slightly greater than 0.05, so maybe we might want to look at that in a bit more detail. But the other two treatments have got a p-value which is way above 0.05, and there's little indication there that there's any significant effect of these treatments. We then find that age class has a significant effect when we're looking at our controls. So unsurprisingly, older people have higher blood pressure than younger people, and we can see that in our controls here. But then we have the p-values for our interactions, and you can see that one of those is highly significant. So treatment B causes a significant reduction in systolic blood pressure, but it only does it in the older age class. And that's how these interaction terms work. The interaction term means that the effect of one factor depends upon the levels of the other factor. If we go back to our data and we look at those differences between the age classes for the different drug treatments. You can see those differences reflected in the p-values we've just seen. If we look at treatment C and we compare that with our controls, you can see that there's very little difference in the effect of age class on systolic blood pressure in those two treatments. If we look at B in the middle, you can see there's a tiny difference there, and that's reflected in that highly significant effect that we saw only for age class 70 to 80 of taking treatment B. Okay, let's summarize what we've seen. It's all a bit complicated, so let's try and get an overall picture. If you've got a single factor ANOVA, the coefficients give you the effect size for each factor level compared to the reference level. And if the reference level doesn't make sense, you can change that using the Relevel function in R. When you've got a two-factor ANOVA and you've got no interaction, then the first set of coefficients work in exactly the same way as for the single factor ANOVA, but then the coefficient or coefficients for factor 2, if it's got more than two levels, tell you the effect of that factor, but that's the effect of that factor for every level of factor 1 because there's no interaction. And then when you've got something like a two-factor ANOVA with an interaction term, then once again the first part of the coefficients table works in the same way, but the second part is very different, so we need to think about it in a bit more detail. The intercept value of the coefficients table, as always, is the estimated mean for the reference levels of however many factors we've got, in this case 2. The levels for factor 1, so that first part of the coefficients table, give you the contrasts with the reference level for factor 1. The effect of factor 2 is then given to you, but that's only the effect of factor 2 when compared with the reference level for factor 1. And then the remaining factor 2 levels, the interaction terms in the model, are telling us the effect of the levels of factor 1 given that factor 2 is no longer at the reference level. Final word is don't panic. When you're looking at coefficients tables for complex models, they can be quite difficult to understand and interpret. Work through them slowly and methodically and you should be okay. And also think about what it is that you're doing with your model. What are you trying to find out from your statistical model, from your two-factor ANOVA with an interaction? And how does that relate to the coefficients table you're looking at? Can you use the coefficients table that you've got to answer the questions that you want to answer? If not, think about doing something like using Relevel to change the reference level for your factors, and maybe that will help. Okay, thank you very much.